Alright, so you've optimized it, memoized your components, and your app still lags when scrolling or typing. That's because performance isn't just about re-renders. It's also about how you handle large UIs and user interactions. So let's try to fix that in this video. So normally the biggest culprit of sluggish apps are these large lists with hundreds, if not thousands of DOM elements. React will definitely choke if you render all of them at once. So take a look at this example. I have this list of 50,000 items, and if I scroll here, I should notice some stutter. Actually, I have a good system right now, so maybe you won't see it. Obviously, the DOM nodes here are just single line div tags, but in a real world scenario where the nodes would be complex structures and where an average device using the website would not have a good system hardware, this definitely would be a major problem. To actually see what happens behind the scenes, let's look at the performance profile. I'll go to the performance tab in the DevTools and I'll click record and reload. This will process my app and give me a report on different performance parameters. Since this is a very unoptimized app, it might take some time, so I'll directly skip to the report. So obviously there's a lot of data here and it can get overwhelming at the beginning, but I'll take you through the important bits quickly. Yeah, so what's happening here is we're literally dumping 50,000 real DOM nodes in the browser all at once. The main thread activity is also packed with long yellow bars, if you see here. That's JavaScript doing heavy work, creating elements, computing layout, and triggering style recalculations. You can also see the solid red block here. These are long tasks. They are bad because they block the main thread for too long, making your app unresponsive. Below that, take a look at this nodes line. So you have this green one, right? This nodes line represents how many DOM elements are in memory. So it climbs fast and stays high because all 50,000 elements are mounted at once. Now you see here that it says 100,000 after a while, 41,000 here, and it eventually jumps up to 100,000. That's because Chrome internally handles nodes differently. Even I'm not exactly sure here how it works, but I remember reading it somewhere that it also treats the text node for item as a separate node. So this item 86, right? This is a separate node and the div that is wrapping this is a separate node. But in the actual elements tree, it would be 50,000 plus a few parent nodes. So no need to worry about this number. We also see a small rise in the listeners line, this yellow one, which would go up even higher if we had event handlers attached to each item. In a real world scenario, almost always these list items do have event listeners for click, hover, or something similar. So this would have also went up if we would have attached event listeners to each of these items. Down at the summary, we have got almost 2 seconds of scripting, 600 milliseconds worth of rendering, and almost 8 seconds of total main thread time just for rendering a list. So bottom line is this is a very memory heavy CPU blocking mess, which is definitely not ideal. Now let's solve this problem. The solution to this is virtualization, and obviously there are a couple of libraries out there that can help you with it. We'll use React Window because it has a simple API, but you can use any of the popular ones out there. Let's quickly install React Window in our project. I'll be installing React Window and one more utility library called React Virtualized AutoSizer. What this utility library does is it automatically scales the React window size to its container. So now that it's installed, I import and tweak our example a little bit. So what I've done here is I've imported the fixed size list from React window and AutoSizer from the utility library. I have put it inside the AutoSizer, and this AutoSizer is wrapped with a div element that has these fixed height and width properties. Because AutoSizer is going to take those values from its container, that is why I've set it to 100 viewport height and 100 viewport width. The list is being rendered inside this AutoSizer, and I'm passing in the item count as 50,000. So let's go back to the browser. Now, if you see in the element section, if I scroll down, it's not going to breach that limit. You will have that many elements, and that is how virtualization works. Now what we'll do is we'll again go back to performance and we'll create a new profile. So I'll again do this and let's scroll through these items. It's going to create a profile for me, and hopefully this time it's going to be much quicker. This time the difference in the memory graph is instantly obvious. That's because with virtualization only the visible rows are rendered, not all 50,000 of them. As you scroll, old rows get recycled and reused. Also notice how the main thread now has shorter yellow bars. Scripting is much lighter. There are fewer layout recalculations, fewer DOM insertions, and less overall work. Even though the total scripting time here is almost 1.2 seconds, it's spread out and much more incremental. There are no massive blocking spikes. The JS heap line still rises, but much more gradually, and it actually comes back down. That's a sign that the garbage collector is able to reclaim memory thanks to fewer elements being mounted. The nodes graph also grows incrementally. This is what you want. Only the visible items are added to the DOM, and as you scroll, they are reused instead of being created from scratch. So you see here that the count is staying at 186 and it's actually growing. This is not something that you should be worried about. Ideally, it shouldn't be there because at any given point, the number of nodes are limited. Even in the elements tab, if you see, you'll only have a limited set of elements. This performance profile is actually not fully up to date. DevTools sometimes counts nodes still in memory even if they are not in the DOM tree anymore. It also doesn't reflect the garbage collected nodes immediately, so the reported count can lag behind the actual DOM reality. But what truly matters here is the reduced count. So that you can clearly see here. We were at like almost 100,000 back in the previous profile, but now we are at like 186, 200, somewhere in that range. So if you're rendering a large list, whether it's a contact list, search results, or a product catalog, and you're not using virtualization, it's going to be messy. Memory usage will skyrocket, your app will feel sluggish, and so will your users. Alright, moving on to input handlers. So you'll normally see a common trap with input handlers, which is triggering updates or API calls on every keystroke. So take a look at this example. Every time I type in something, the handler runs and so does the API call. Let's pretend that it's an API call for a second. This is unnecessary and floods our backend for no reason. So let's try to optimize this. We can implement either debouncing or throttling here. So debouncing ensures that a function is only called once after a specific delay after the last event. So if I type a bunch of characters and say the time difference between each character that's typed is less than 500 milliseconds, I'll skip that event and its callback altogether. That way, when there's a good amount of gap between what user is typing, only then we'll make a backend call. This prevents a lot of unnecessary requests from going through. Throttling again is similar. It ensures that a function is only called at most once every specified interval, no matter how many times that event is triggered. So for instance, you handle a scroll event only once every 200 milliseconds, even if it fires constantly. So in a second, even if scroll event triggers for like 100 times, 5-ish events will go through. I have created my own custom hooks for debouncing and throttling. If you want to know how you can create one yourself from scratch, you can watch my video on debounce and throttle polyfills in which I have covered each step in detail. I have written those functions in JavaScript in the videos, but the overall logic is pretty much the same. So I'm not going to go through each line here. Let's just assume that we already know what exactly goes inside a debounce polyfill and a throttle polyfill. You'll find the links for both of the videos in the description. Now, instead of calling the API directly inside this onChange handler, we'll wrap it in the hook and then pass that to the handler. So what I'm going to do is add a debounced API call. This debounced API call is going to use the useDebounce hook that I've created over here. Let me actually import all of the missing imports. And instead of directly making an API call here, what I'm going to do is call debounced API call. Let me also pass in the actual value. Let's get rid of this. And we are now going to debounce this API call. So if I go inside the browser and I try to type in thousands of characters all together, only one API call goes through. Let me clear this and do it once again. I'll clear all of it. Now I'll type in things pretty quickly and only one API call goes through with this value. Similarly, if I replace this with throttle, So instead of useDebounce, I'll use useThrottle and save this. Now if I type in something, you'll see that it's not being triggered for all of the characters. I have at least let me see how many characters I have in this string. If I check the length, it's like 72 characters, but only a handful number of API calls actually went through. So yeah, debouncing and throttling definitely help, especially in case of events that get triggered a lot. So that's definitely a performance boost. Now that you have looked at virtualizing large lists and optimizing user input, I also should tell you about these two React hooks that try to do something similar. I'm talking about useTransition and useDeferredValue. useTransition lets you prioritize urgent updates and deprioritize non-urgent ones. So normally when you have a huge list of items and a search bar that filters through it, there's a chance that the user input might feel laggy because state update blocks the main thread. This gives a very bad user experience, and useTransition helps you solve that by prioritizing UI update, which it treats as an urgent task. It deprioritizes state update so that the actual list might get filtered after like 500 milliseconds. So you essentially get a similar experience like debounce. You can also show like a pending state so that the user is aware that some filtering operation is happening in the background. useDeferredValue is again very similar, but if you have implemented virtualization and debouncing already in your app, to be very honest, I don't see a point in using these two hooks. I'm sure there are niche scenarios where using these hooks would make more sense, but I have personally not come across those scenarios ever. Even if I do, virtualizing them and debouncing user input events solves 99% of the problem. So yeah, if you want to learn more on these hooks, I have a separate video covering them with code examples, which I'll link in the description. You can go check them out. Alright, that should help you solve your janky UI problem. User interactions are literally the most important part of your app. If a user gets even a slight delay for any interaction they perform, chances are they won't stick on your platform for long. To do that, you have to be efficient in terms of number of items you have on your page. You also have to prioritize and deprioritize events based on the value a user can get out of it. So hope this video made sense. In the next one, we'll look at some advanced strategies on improving your app's performance like code splitting, bundle analysis, hydration, dynamic inputs, and we'll even glance some parts of server components and server-side rendering. So do subscribe for that. Do give this video a thumbs up, and yeah, I'll see you in the next one.